Hello everyone, we're back to section 6.3 and here we're going to be talking about interest rate swaps. So the goal of this session, we're going to define interest rate swaps and then just derive again the pricing formula for these swaps. So sit tight and enjoy. Head and talk about interest rate swaps. So first thing first, I'm noting what we found from our previous video on the 4-hour interest rates. We were able to derive this equation. And then from this is exactly equivalent to the equation that we have here. So let M be a number between 1 and capital N. What we're calling an M-pair swap is a contract that makes these payments at S1, S2, Sm at time 1, 2 up to M, where the cash flow is defined by this relation, where K is the constant and Rn minus 1, of course, is stochastic. This is the interest rates prevailing at time N minus 1. So to better explain this, it's good to look at to have a look at our timeline again. So for the swap, we have at time 1, we're receiving a K, which is constant. And then we're paying out an R0, right? And this is basically S1. And if you replace here by 1, we have R0 here. So that's exactly what we have. So K is constant again, and note how R1 is stochastic. It can change from time to time. And we have Rn, etc. up to the last time period M here. So now to be able to price this contract, naturally what we need to do, we need to take each of these cash flows, right, the separated cash flow, and then discount them to the present. So this is going to be discounted by D1, and the cash flow occurring at time 2 is going to be discounted by D2, and then we just do the summation, right? And that's exactly what's happening here. Here we're summing some cash flows, the cash flow occurring at time 1 up to time M, and this is what you're discounting. To discount the cash flow occurring at time N, we're multiplying by Dn. That is what this is meaning. And what the cash flow is just like the simple K, which is constant, minus this Rn minus 1. So I think this formula makes a lot of sense. So now we're just going to do a set of algebra to see where this does get us. So first we can distribute this Dn inside here, right? And that's what we have here. This Dn has been distributed. Then naturally we can also put this expectation and then put it inside here, right? And distribute the expectation as well. And that's all that has been done here. Then as a next step, here, this expression is exactly the same as the one we have here. The only difference here is that we're adding a number, dn, and then we're subtracting a number, dn as well, right? So nothing has changed. We can absolutely do this. Then next step, when we do that, then we can take this, let's say this, we can take out this expectation first, right? That's why we're seeing these two expectations. And here we can essentially factor out the dn. So that is dn 1 plus Rn minus 1. This dn has been just factored out. And that's exactly what we have here, right? And then when you distribute the expected value here, it just comes, you have that, right? And then, well, notice how this thing here became dn minus 1. So why is that? Well, if you remember the definition of dn, right? The dn is just 1 divided by 1 plus R0 multiplied dot 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 up to 1 divided by 1 plus Rn minus 1, right? And then, so this is the definition of dn, right? So when we take dn and we multiply by 1 plus Rn minus 1, what we have is these two cancel out. And essentially we have this thing, essentially this was like the last one that was here basically was 1 plus Rn minus 1, all right? So then that means that this just can become dn minus 1. And that's exactly what we have here. So next, so if you look closely, expected value as of time zero of dn minus one, that is nothing but this expression here, right? It's just the price of the zero coupon bond, paying $1 at time n minus one. And this is nothing but the price of zero coupon bond, paying $1 at time n, right? And from here, we can replace it by this expression. So what happened is, when you look at this, right, we can replace it by this thing here, right? So in our case here, the n that are in the front was 0. So that means if this is 0, if this is 0, that means this needs to be 0, this needs to be 0 on this side. And we take this, that's exactly what we have here, right? And also, obviously, this m here is n minus 1, right? So this m here becomes n minus 1. That's all we have here. We just use essentially this relation. And then, as you can see, we are able to find a way to price swaps. This is the value of the swap. And we can also see this is the same. This is also interesting here, right? Because here the value of the swap is just some type of linear combination of zero coupon bond prices. Exactly. So here, when we just simplify, oh, sorry, we don't simplify. What we're doing is we're factoring out this b0n. That's why we have this expression here. Okay, so then one thing that's interesting, we seen before on this binomial tree, right? And on this binomial tree, we're able to price all these zero coupon bonds that we wanted. And turns out that when we look at closely here, we were not only able to price zero coupon bond, we were also able to price 4R rates, right? And what we're seeing here is the swap is nothing but a linear combination of zero coupon bonds and 4R rates. And or even if you look here, when work class, it's only a linear combination of zero coupon bonds. So what that means that you now know how to price swap rates swaps on this binomial tree as well, because it's just reduced to a problem of pricing zero coupon bonds. All right. So thinking about what we have, let's just now do the recap. What we did was simply to define interest rate swaps. And then after that, we derived the swap pricing formula. And we have shown that also now we know how to price these swaps on the binomial interest rate tree model. All right. Thank you, and see you in the next video.